So you can see the screen, right?
Yes, sir.
Yes.
Okay, okay. So yesterday we have started with what actually a TDM and followed by pulse width modulation. And the generation of pulse width modulation block diagram, we have a sample and hold circuit followed by an adder. The adder output is given to a comparator. And I said comparator output is my PWM. If I give PWM as input to the monostable multi, PPM can be generated. Let us see whether we really generate the pulse width modulated signal or not. So I take a sample M of t. I take a sample M of t, something like this. Let it be M of t or S of t, whatever. S of t. This is my input signal to which I have to generate pulse width modulated signal. So therefore, what I do is, let us follow the block diagram. So we have given the input signal S of t, and I have a sample and hold circuit here. The job of sample and hold circuit is it collects the sample and that value held for a certain time period.
Hello, sir. Sudhir, sir.
Now you can hear me, right?
Yes, sir. Yes, sir.
Yes, sir.
Okay, okay. I'm sorry, my laptop battery is dead. I forgot to switch on the charger. So the sample and hold circuit, it collects the sample and holds for a duration of a certain time period. So that certain time period is our sample interval Ts. So now assume I want to collect samples at regular intervals of time, let us suppose. Something like this. So here also. So initially I collected the sample. So that value will remain till the next interval. Then my M of t is decreased. So that decreased m of t will remain. Again, my m of t is decreased. So that decreased m of t will remain till the next sample value. Again, it is further decreased. Okay. Now here it is compared to the previous sample. Now it is little increased. Let it be. And now here I got something like this. Let us suppose. So this is the output of the sample and hold circuit, that is S2 of t. Check. S1 of t. S1 of t. Okay. Fine. So access this time. Now S1 of t is given to the adder. What is the other input to this adder?
S2 of t minus 1.
S2 of t minus 1. What is S2 of t?
Sawtooth.
S2 of t is a sawtooth waveform, and this is my S2 of t, and S2 of t minus 1, this is my S2 of t. The sawtooth is shifted towards the negative side. So therefore, let me draw that S2 of t also. This is S1. Let it be S2 of t 0 minus 1. So I'm taking the same sample time interval. Okay. So I can have something like this. This is my sawtooth waveform. This is your S2 of t minus 1. Sorry, this is S2 of t minus 1. Now, what we are doing here after S2 of t minus 1, we are adding S1 and S2 of t minus 1 to generate S3 of t. So S3 of t equal to S1 of t plus S2 of t minus 1. That means we need to add these two signals, S1 of t, S2 of t minus 1. If I add these two, okay. Let me draw the waveform, addition of these two signals. Now, during this interval, or my signal will be, I can say something, it is moving like this, right? So initially the m of t or s of t value is large, slowly it is decreasing. Now during this interval, because my S1 of t is large, and here I have a sawtooth waveform, during this interval, if I add these two, because after all this is a DC value, therefore this entire sawtooth will be shifted upward. So therefore, my sawtooth waveform after addition will be something like this. Because now here I have a negative edge. So my sawtooth is, or because I have a decrease in S of t, so I have the negative edge or the reverse edge will be thrown negative, something like this. Right. Now during the second interval, during this interval, compared to the previous voltage level. Now this voltage level of S1 of t is less and is added to S2 of t minus 1. Therefore, this will be sorry. This will be like this. So this is decreased. Try to observe the difference between these two levels, because here the level is more, my sawtooth is high. Here the level is less, my sawtooth is at low value. Again, during the next interval, I can have similarly. Are you following me?
Yes, sir.
Something like that, I can get my signal. Now, so this S3 of t is now given to a comparator, right? And my threshold value of the comparator is 0 volts, let us suppose. Threshold value of comparator is 0 volts. That means if my S3 of t is more than 0 volts, if my S3 of t is more than 0 volts, then my output, the threshold like fixed at 0 volts, then my output will be plus 5 volts or say plus 3 volts. Otherwise 0 volts. So therefore, as long as my input is positive, so as long as for the duration the input is positive till this point, I can have a plus 5 volts, something like this. Now from here to here, I don't have because it is less than 0. So my output voltage of the comparator will become 0. From here to here again, I have some till this point. Are you following me? Am I clear to you?
Yes, sir.
Now this is the entire negative zone. So my comparator output would become 0. So from here to here, again, my comparator output will be active high. And from here to here, my comparator output is active high. And from here to here, my comparator output is high. Now, this is my S4 of t. Fine. Now have a look at the width of the pulse of S4 of t. Here, the pulse width is very large. Here, the pulse width is decreased compared to previous one. Here, it is further decreased. Here, it is further decreased. Now, there is an increase in the width of the pulse. Further, there is an increase in the width of the pulse. And the width of the pulse of S4 of t is in accordance with the variations of the M of t. Are you following me? Is that clear?
Yes. Yes, sir.
So this is how we modulate a pulse width. We generate a pulse width modulated signal. Any doubt till this point? Till this point. Okay. Okay. So now let me extend my discussion with the generation of PPM also here itself. That is my S5 of T. So I have a sample here. And I have another sample here. Somewhere here. Again, somewhere here. Somewhere here. Somewhere here. And somewhere here. Now I said, I explained the concept of what is monostable multi yesterday. So when there is an input, when there is a triggering input for monostable multi, when there is a triggering input for monostable multi, it generates a pulse. That is what we call it as quasi-stable state. It generates a pulse. Now, here I said when there is a negative edge, and when there is a shift from high to low, my monostable multi is triggered. If that is the case, look at here. My S4 of T is the input to your block diagram. S4 of T is the input to your block diagram. So sorry, S4 of T is the input to the monostable multi. So therefore, I have this is my negative edge. During this interval, when there is a shift from positive to 0, high to low, that is what we call it as a negative edge. During that period, my monostable multi is triggered and during that period, a pulse is generated. Now here also if you observe carefully. Then here a pulse is generated. Here from negative to positive. Again, there is a increase in width. Therefore, again there is an increase in width. Now, if you observe carefully, because my S of T or M of T is large during the first sample, from the reference or relative position, there is a maximum shift of the pulse. The position of the pulse is shifted maximum. And from here to here, there is a little less when compared to the previous one. So on and so forth. Slowly it is decreasing. Now again, if you observe here, my amplitude is increasing. Therefore, the relative position of the pulse is now increased further from here to here. Still further increased. So this is what we call it as pulse position modulated signal. Clear? Is that clear?
Yes, sir.
Okay.
Yes, sir.
Okay. So we started with PWM, how a PWM waveform will look like. Then we got the block diagram of what we call it as PWM, generation of PWM, and of course PPM. So for generation of PPM, if there is a question how to generate PPM, Some people, what they do is they simply write, instead of drawing all the block, they simply write, I have a PWM modulator. Okay, this is my PWM modulator. Output is given to a monostable multi. Okay, so this is my PPM. This is my S of T. Even then also, you have to draw all these figures because we are generating the PWM signal, then we are generating the PPM signal. Okay. Subbarao sir. Subbarao sir. ఉన్నారా సార్?
ఉన్నారు సార్.
Okay. Let us move to the last topic of unit 1. Can anyone tell me what might be the next topic or the last topic of unit 1? What is left over? What we haven't seen till now?
Pulse digital modulation.
No. I'm asking unit 1, unit 1, unit 1. See, in unit 1, we started with PAM. In PAM, we classified into 3 types: instantaneous, natural, and flat top sampled PAMs. And we discussed about all the 3 how to generate. After that, we discussed about how to demodulate a PAM signal, whether it is a flat top, whether it is a natural sampled PAM, whether it is an instantaneous sampled PAM. Right? Now, having seen the generation and demodulation of PAM, then we slowly shifted to time division multiplexing, how a PAM signal can multiplex more than one signal over a single channel. After that, we shifted to the very next topic, how to generate PWM, pulse width modulated signal. A little extension to generation of pulse width modulated, we generated pulse position modulated just now. Now my question is, what is left over?
Demodulation of pulse width modulation. Demodulation.
Perfect. So modulation part we have seen. So the very next topic is how to demodulate a pulse width modulated signal and how to demodulate a pulse position modulated signal. Okay, so that is the only last topic left over for unit 1.